Yeah, thank you very much for the introduction, and thanks a lot for inviting me to this beautiful conference, very stimulating. So I want to tell you a little bit about the work that we do on quantum optics without actually using any optics other than to define our system. So it's a system of emitters that don't emit photons, but they emit atoms. So we basically play the atom optics analogy here of interchanging light and matter. And so, I mean, the whole thing you can see in terms of a paradigm of quantum simulation. So you have a system that you're interested in, but you're actually not studying that. You're studying instead a simulator. And what's nice is that you can tune the Hamiltonians. Now, in our case, the system will be a waveguide QED. And our simulator is our matter wave simulator. And of course, you could object here saying, well, I mean, usually in quantum simulation, you want to have a system that's much simpler than the system that you want to study. Now, in terms of quantum optics, the Hamiltonian itself is, of course, very controllable. And so one could raise the point, why do this? If you sort of don't have more control than you might have in a quantum optical system, after all. But I mean, quite in general, I think it's nice to sort of look at the phenomena from different angles. And so what we have here is a system where we can realize Hamiltonians that look just like usual light-matter interaction Hamiltonians. And so they show a truly radiative behavior. We can control actually here the vacuum coupling very nicely. We can realize systems of many identical emitters. And what's particularly nice is that the Purcell factor in these systems is infinite, or the beta is basically 1. So we don't have to deal with any effects of unwanted couplings to the environment that one would otherwise need to take into account, which of course could be an advantage somehow. You can use it, dissipation. But I mean, we have here a very clean system where we don't have to worry about channels of decay that we are not actively addressing. Of course, the drawback is, yeah, it's no direct technological relevance. But we're interested in fundamental physics and sort of want to explore what happens in novel regimes. Okay, so how can one implement such a quantum emitter? I mean, this is a very primitive slide. I apologize for the kind of quality, but I mean, the basic idea is that if you look at the two-level quantum emitter, in a very naive way, it's basically a container for a photon. Yeah? So the photon is either inside or it's not, yeah? And what makes it come out is a coupling to the vacuum fluctuations in spontaneous decay. The photon will have energy, will have a wavelength. The two are related through a dispersion relation. Now, if you can just build a system now where you say I have a container, just I have here, but what's inside is not a photon, it's some other particle. Yeah, so in this case, it's an atom. There's going to be some vacuum coupling, and there's going to be some emission of that particle as a result of this vacuum coupling. Now, here what comes out are the Broglie waves. So we are interested basically in the kinetic energy of those. We are not interested in the rest mass of the atom. So that's something that actually you can just subtract out. In the end, you have the Broglie wavelengths corresponding to the photonic wavelengths here, and you have a dispersion relation. Now that's massive particles that come out, so it's different from photons in free space, of course. But if you consider photonic bandgap material and you're close to the edge, then the photon gets an effective mass, and so the dispersion relations are the same. And so in that sense, you can use this system, if you can build it, to study the effects of coupling to photonic bandgaps. Okay, so what are the ingredients? They're pretty standard. You use atoms. So in this case, rubidium. You pick two hyperfine states. You couple them using microwave radiation. And then what you do is you put this system, or this atom, you put it in an optical lattice. Each lattice well now acts as an emitter. And what's important here is that the lattice only acts on one of the states. It doesn't act on the other one. So, and then to detect, you can now detect how much is left in your emitter. After a while, you can detect what's coming out through time-of-flight techniques. Okay, so yeah, so we did this a few years ago for the first time. So here's the Hamiltonian. Yeah, so if you just couple, you get the Rabi coupling. Now you put one of the states into a well, and then you have a whole range of kinetic momentum states that are available for the other state that you can couple to resonantly. Yeah. And if you write down the Hamiltonian, it looks like this. Yeah. So you go basically you take a red atom, you put it here from the well into a vacuum in some state labeled by the momentum, and so you have a whole range of them. You sum up coherently. And so the strength of this happening is basically your vacuum coupling. Effectively, now that's just the coupling that you apply. And so the Hamiltonian is exactly analogous to Weisskopf-Wigner. Yeah, so normally what couples is the dipole coupling to the vacuum field, the resonant vacuum field. In our case, we have just this one coupling term. And so we sort of take this product and just handle that separately. Yeah. So what is now the emitter? The emitter is the well. Yeah. The atom, when it's inside the emitter, we call it an excitation of the emitter, and when it comes out, it becomes radiation. Okay, so.
The red level is the ground level?
So it doesn't really matter, because if you go into a rotating frame and you control the detuning of your coupling, you can sort of shift red and blue around. Yeah? So typically we operate here that we shift red above blue actually. Yeah? And so you have basically this is your excitation energy above ground. Yeah? And so you can control this excitation energy by changing the detuning. So we can change the vacuum coupling easily, and we can change the emitter energy easily. Okay, so all kinds of regimes are accessible, ranging from conventional Markovian decay to cavity QED, essentially, where you sort of, if you control the mode or the bath, you can structure it. Yeah, you can do basically. You can study photonic crystals, or you can just go to strong coupling. So all these regimes are accessible. Yeah, so here's just some quick rundown what you can do. So if you have weak coupling, you see exponential decay. If you have strong coupling, in extreme case, you have no energy here, no excitation energy, just coupling. Yeah. What you see is that you get oscillatory behavior, so it's a non-Markovian dynamics simply because of strong coupling. So the radiation is so slow that it basically has no chance to escape, gets sucked back in, and then sort of oozes out only slowly. And then also something is left, and what's left there is an offset, and that's an atom photon bound state that one is coupling to. Yeah, so I mean, this is a very old kind of topic. It was first discussed in the early 80s by Eberle and Levenstein, Rozhashevsky, in terms of ionization phenomena, basically bringing something from bound state into continuum. Okay, so we can look at what's left in the emitter, but we can also look at what's coming out. Yeah? So what you see here is a representation of a time-of-flight spectrum. So this is so what's happening is we emit, we turn everything off, things fall under gravity, and if something comes out, it will fly to a certain position, and that's where we detect it. Yeah? So in this case, because it's a symmetric situation and we have many emitters, you see a blob here and you see a blob there. Yeah? And so these blobs, they have now, the momentum depends on the energy that you apply in your emitter, and so what you see is that there's a parabolic dispersion, which is of course completely expected. Yeah? And then sort of you see also that it gets narrower here, so the line width basically gets sharper and sharper the farther or the more Markovian you become. Now, yeah, so when control this, what's weird here also is that we can sort of see emission at negative energies. So this means it's very simple. You pull the excited state below the ground state, which we can do in our system. Yeah. So now the ground state or the excited state lives below the continuum. Yeah. And so now if you, and it's exactly the same situation as for not photonic band gap, by the way. So yeah, so if you decay, by definition, brings you from E to G. So if you increase your energy in decay, it means that the radiation comes out has to have negative energy, which is kind of weird if you think about it this way. But negative energy just means that because of the dispersion relation, that this momentum is imaginary. In other words, you get an evanescent wave that's sort of unable to escape. And we detected that, or if you fit sort of your momentum distributions, you can compare this to calculations, and it actually fits quite nicely. Okay, so that's our system. Yeah, so this is a atom photon bound state, or in our case, matter wave emitter bound state. And the range of it depends, of course, on how strongly bound it is, and this binding energy depends on how far below the edge of the continuum you are. So typically, in our case, these emitters are tuned such that the evanescent tail just leaks into the next well of the optical lattice. So the closer to the edge you go, the bigger it gets, but also the more sensitive to the tuning fluctuations you will become. And those states are magnetically field sensitive. So already now we're basically sensitive to fields on the order of 10 or 100 microgauss. And so it becomes harder and harder the closer you go, you get to the edge. Okay, so yeah, so we have fractional decay. That's sort of what's left. So this emitter sort of surrounds itself with a cloud of these matter wave excitations.
Can you perhaps explain
Yeah.
what is fractional decay?
Yeah, so fractional decay is basically, I mean, very simple is when you turn on your vacuum coupling, there is basically a bunch of radiation that escapes, but then there's also something that's left, yeah. And so essentially you have a lamp shift, yeah, and you have a dissipative piece, and the lamp shift is connected to the formation of this atom photon bound state. And so in some sense, I mean, what we can do here, and that you cannot do in reality with a real quantum optical system, is we can adiabatically ramp up the vacuum coupling, and then you can smoothly grow into this bound state without actually emitting anything. Okay, so yeah, in photonic bands, this is actually the physics that you also get. Yeah, so if you are below the edge, you get this atom photon bound state, and that can mediate this kind of coherent spin exchange interactions. And if you are above resonance, you still have a one-dimensional environment. This means that the intensity of the radiation that gets emitted doesn't decay, and so you get strong couplings between emitters that are far apart. Okay, and so yeah, this all ties into this big field of waveguide QED. I mean, in the optical domain here with atoms, as we have thought about, or silicon vacancies or quantum dots, and then also, of course, same physics happens in a microwave domain. Okay, so now to this topic of super and subradiance. So as you see here, I mean, our emitters are wells, yeah, and we have a lattice here. So this means that by definition, a well that has a red atom in it is excited, and an atom that has an empty, or is empty, the well that is empty, has no atoms in it, is in a ground state. And so we have a whole range of them. They're all coupled to the same radiative environment. And so this means we can now prepare initial states that have particular behaviors once the Hamiltonian is, or the vacuum coupling is turned on. Okay, and so just, I mean, this is very standard, but still good to sort of start with this decay sort experiment. So if you have a single emitter and you turn on the vacuum coupling, you get exponential decay. If you take a second emitter, you put it very close by in the ground state, what you see is, you have one excitation now, two emitters. What you see instead is you're decaying to 1/2, and the rate at which this happens here is increased. And so the reason for this is that you can write this situation here in terms of a symmetric combination and antisymmetric combination. Decay here leads to the ground state. You have two possibilities. They constructively interfere, if you want, and so you get a higher intensity of that, or the rate is increased. This thing destructively interferes and cannot decay. So that's a superradiant state, that's a subradiant state. Okay, now if you have emitters that are not at the same position or within the wavelengths, then, I mean, in 1D, you still get exponential decay for a single emitter, but if you put another emitter, it now matters where you put it. Yeah. And so, in general, we will write the situation again as a combination, a symmetric and antisymmetric, basically, and so I'm just keeping this here general as a phase, in here. And so when radiation comes, yes, it will pick up this phase, but also because the emitters have a distance, there will be propagation phase that's associated, or that's or that has to include in this phase. And so the total phase that matters is that phase that one has in the beginning, so whether it's symmetric or antisymmetric or anything in between, and then what kind of propagation delay that is. And so when this total phase here is 0, you expect superradiant decay, and when the total phase is pi, then you get destructive interference, and so you get no decay. Okay, so I mean, these are known as time decay states simply because they are excited usually with a weak laser beam that sort of propagates through the sample and prepares these emitter phases. Okay, so now in our case, we don't have real emitters, we don't have a laser, but what we have is a control over the initial state. And so something that we can prepare is a superfluid, or a coherent state. So in this coherent state, every atom is distributed over all the wells. And those atoms are independent of each other. So now if you pick one of those, you basically have the equivalent of a time decay state with 0 phase. So the excitation could be here, or it could be here, or anywhere else, and it's a coherent superposition. And so we did the experiment with that. So first of all, we started with the thermal gas as a reference, so we basically heat everything up, and so we end up in the situation that we had before, where you have basically this parabola. Now, if you do this with a superfluid, what you find is that this parabola is no longer traced out everywhere, but you get these blobs. And so there's basically regions where you have, let's say, more than before, and then there's regions where you have less than before. And so if you look at the conditions here, the Broglie wavelength is equal, the same as the distance between the emitters, so that gives you constructive interference, and here the Broglie wavelength is twice the emitter distance, and that gives you destructive interference. So that's superradiance here, and that's subradiance. Now, we can control these phases simply because what we can do is we can imprint the phase gradient across the sample of emitters, and that's very simple because our tubes are vertical, and we can just sort of apply gravity for a while, and that will sort of imprint the phase gradient depending on the vertical position. And so if you do that, what you see is that those blobs start moving around. And so you can sort of tune your system around to an extreme case where you were superradiant before, you are now a subradiant, or where you were subradiant, you are now superradiant, or you can also have situations where you are emitting to one side only, so you're superradiant going out this way and non-radiant or a subradiant going out the other way. So it's a directional effect. Of course, the direction is already imprinted basically in the phase gradient, so it's all characteristic of the initial state. Okay, so now you can also look at dynamics. And so what we did here actually is we parked ourselves in this situation. We parked ourselves here at the subradiant detuning. And so what you see here is a single emitter behavior. So that's what you get when you have no collective effects. And so actually it starts out pretty much like a single emitter, but then it gets faster. Yeah. And so you can actually fit this with a rate, here an initial decay rate and a later decay rate. And this initial rate, I'm sure it's only 3 points, but the rate agrees, or you can see it here. Yeah, so the behavior agrees with the single emitter prediction, and then after it gets faster. And so why is this? It's because the radiation is very slow. Yeah? So we're not talking about 10 to the 8 meters per second here, but we're talking about maybe a centimeter per second. Yeah? And so it takes, if you take the distance between emitters, half micrometer or so, and you see that it takes tens of microseconds to reach the next emitter. And so that's exactly when we sort of calculate things. Yeah, this is a direct simulation. You see that the time at which this kink happens is the time when the radiation has reached the neighbor. Yeah. And so it's clear that you can only get superradiance if the emitters know that there's another emitter close by, and so it takes this time to speed up. So this has connections to a superradiant paradox. We have Kanu here. It sort of could give rise to an even enhanced rate depending on how strong this effect is. Yeah? So in our case, it hasn't decayed much, and then we already reached the next emitter. If you wait longer, you can sort of get more of an enhancement here of this decay after that even. So, but yeah, it's non-Markovian in the sense that it's not exponential. You see these little wiggles here, yeah. So they are basically non-Markovian remnants because of strong coupling. Yeah, so we are not very weakly coupled here. Now you can also look at the subradiant detuning, and what you see here is a single emitter prediction again. And so what we see is that the excitation sort of does not leave the emitter. There is a little oscillation here, and so when you analyze this, and so my student here, Alfonso Lanuza, did this very carefully, you find that basically that what dominates here, so it's different effects that contribute. There's poles, and there's a bound state, there's subradiant, bound state, and superradiant state. And so the main contributions is basically a subradiant state and the bound state at the edge. And so these two things basically beat against each other. Yeah? And so this subradiant state is actually a state where the radiation, if you see here in blue, is sort of concentrated between the emitters. So it's a kind of bound state in the continuum where the emitters act basically as mirrors and the radiation is trapped in between. And then this bound state here is simply because of the formation of atom-photon bound state from the coupling to the continuum edge where we are relatively close by. And so this oscillation is basically a beat between these two. Yeah. So we can sort of, from this calculation, we can again sort of calculate what the radiation should do spatially, and we get out this simulation. Yeah, so this is momentum as a function, momentum distribution as a function of time, and we can compare this to measurement, and you see the agreement is pretty good. Yeah, so we're pretty confident that that captures the physics. Okay, now we can also start not with a superfluid, but with mod insulator. And so this is now relatively easy to see that this should be a fully inverted state. And so you would expect super-radiant burst, and so on. And so, yeah, if you just look at this in a very simple two emitter scenario, so you start with a fully inverted system, you decay spontaneously, you form this, again, superposition state, and then this superposition state decays with a larger rate until you reach the bottom of your ladder. Yeah? And so the point is that the first emission brings you into coherent superposition. Okay, so fully excited state is mod insulator, and our emitters, yes, are wells, filled or not filled, so a decay brings us here into this situation. Now notice, because we are at a distance, yeah, we also get the phase, which is not zero, and then we decay from there. And so this phase coherence here, this is basically induced by the decay. And there's one quote I found from a paper by Dickey where it says the memory. So this was a discussion of a coherence-brightened laser. Yeah, we have sort of discussed the connection to superradiance. And it says the memory of the direction of the emission of the first photon is burned into the energy level structure of the radiating system. Yeah. So I think this is what this burning means. Yeah. So you basically leave a trace in the excitation of your medium, and this trace can have momentum. Yeah. Okay, so we started this decay, and so we were first very disappointed because what we do not see is a significant increase of the decay rate. Actually, no increase at all. Now, one has to be a little bit careful here. The coherence length of the radiation that we can get in our tubes is very small, simply because the tubes are very strongly confining. So in some sense, if you put a few excitations in the tube, free atoms, they form some kind of Tonks gas almost. Yeah. So the coherence length is reduced. So our expectation is basically, if we take the coherence length of two wells, is that, yeah, we should start single particle, and then we should get faster a little bit, but actually it turns out we're getting even slower, and that's because once you decay significantly, you start sort of accumulating the radiation in the tubes. They cannot really escape. It's kind of still stuck there, yeah? And so you get all these interaction effects that come into play. So in other words, we don't want to look at this too far out. But what we can do is look at the momentum distribution. And so if you look at the momentum distribution, and we look very carefully, yeah? So this was not something that we saw immediately, yeah? Is that you get slight changes in this distribution. You see here it's a little bit more triangular. Maybe there's a head here, yeah? And here it's bulging out a little bit. Yeah? And so this is for the, let's say, super radiant detuning. This is for the subradiant detuning. So I mean, it shouldn't really matter, yeah? For a fully inverted system. What the detuning is, you will always burn the correct kind of trace into your system. You will always get super radiance. It's just that these detunings are the ones that we had before. And so if you subtract the two, you see a small difference. Yeah. And the question is, does this here have anything to do with this phase coherence? And so we made a test of that. I mean, first of all, you can compare the calculations, but we made a test, and in the following way. We introduced another state. There is another kind of excitation of the emitter, and this level, or this emitter level, is not coupled to the vacuum. So in other words, if you put yourself into a superposition, the green state will not decay as a function of time. And yet, if you look at the momentum distribution of this green state, you also see it has these features. Yeah? And so you see that for the superradiant detuning, there's something here at 0 phase or 2 pi of phase. And if you are at the subradiant detuning, you see something that's at pi of a phase. And so the explanation is very simple. Yeah? So we start out basically by rotating the excitations to the equator. then red will decay, green will not. And so if red has decayed, you create this kind of superpositions, and that's exactly what should give you these patterns. Yeah. So in other words, there is some evidence here that the system burns, or the decay leads to a burning of the memory into the system. And then that will, of course, enhance itself the further on the decay occurs. Now, all of this was in a Markovian limit here for this inverted state. The question is, I mean, the situation is very complicated, and so, yeah, so it's probably very hard to model this in general. But yeah, so Alfonso is very ambitious in kind of his exact treatments of things, and so he was able to develop an analytic exact solution for two excited emitters coupled to a waveguide that involves some very intricate complex analysis. And so, I mean, what he considered was a single band waveguide, and you see if you're in the center of the guide, you decay basically exponentially, and if you are at the edges, you start becoming very, very non-Markovian. Yeah? And so there's some hope that one can actually maybe see this kind of effects in our system where we have not many emitters that are contributing in the end. Okay, so here just quickly we can realize these kind of photonic bands simply by making the vacuum here slightly structured with an optical lattice potential itself. So we can basically, yeah, we can identify single bands that we are coupling to. You can put yourself in the center of a band. You can sort of study what happens when you increase the coupling, and you see you go from quasi-Markovian decay for weak coupling to sort of Rabi oscillations for strong coupling. And so we have this basically accessible to us to be able to study this kind of effects now with more than one excitation. This was always with one excitation only. And so you see here, this is the behavior that you would get for a single emitter coupled to a photonic band. That doesn't quite describe the situation. So here we have to deal with the fact, of course, that we have many emitters and there's empty ones surrounding the emitter that was excited. And so if you take this into account, you actually, it fits beautifully. Okay, so yeah, with this, I'm basically at the end. So, I mean, the question is always, if you do a simulation of something, can this have an interest on its own, or is it just a slave to the system that you want to study? So I want to basically claim that, yeah, there are some things that are very kind of unique to what we can do. For example, we can vary the characteristics of the bands from, let's say, bosonic to effectively fermionic by just making one-dimensional configurations. And we can also sort of play around with these extra states that I just showed you in green, yeah, that sort of can give you new insights on this kind of phenomena. So just at the very end, we can also go beyond waveguide QED. What we did in this paper here was that we sort of created something that we called matter wave polaritons. So essentially, if you have an optical lattice, the red atoms can tunnel, yeah? But if you dress them with atom photon bound state, they can basically now tunnel around and interact as quasi-particles. And so we realized a bosonic Bose-Hubbard model for polaritonic Bose-Hubbard model. And so you see some kind of fancy features in terms of shift of the phase as a result of phase transition as a result of the coupling, or also you can see there's basically different branches of the polaritons that you can couple to. Okay, and so with this, I'm at the end. Just want to thank my group. So this is a time-integrated picture, so past and present. So the main contributors to the work that I presented today were Yong Shin, he's now a postdoc at Harvard, and Alfonso Lanuza, who is now at the University of Burgos. All right, so thank you.
So thank you for the talk. There is already a contribution.
Thanks for the very nice talk. This is super exciting. So a quick question first. So I recall the value for d over v in your case is around 30 microseconds.
Yeah.
What's the corresponding gamma?
So you're basically asking on the time scale of the decay, sort of how much have I propagated. And so I think for the effects that you're discussing, like enhanced superradiance, you would need this value to be on order of 1 or larger. So we are more like 0.1 to 0.3. Yeah, so it's not in a regime yet where we can really sort of claim that we would see these effects.
I think that should, so we did most of our calculations in the linear dispersion regime, but with Hadise actually we are also looking in non-linear dispersion. So the decay rates in that case for the collective emission were the black curves, were they theory curves, and do you know what the rates might be?
So let me see if I can go back here. So these curves here, that was a simple situation. We took a box, we just put 3 emitters in, we quantized the box, and then looked at the dynamics of a small system. Yeah, but we have actually, Alfonso has an analytical theory for the situation that includes one excitation in an array of m emitters. Yeah, and so you can actually solve this kind of nicely if it takes, say, 2 or 3 emitters. Yeah, so he has some solutions for that. So I showed you at the end this work where we couple to a photonic band, yeah, where you sort of take the empty emitters into account. So that's an initial state where the excitation is concentrated in one emitter. But we can also start out with a situation where it's smeared out over emitters.
And are you also tuning the dispersion in that case?
And
the n-emitter case?
Yeah, I mean, everything is included in that, yeah. So, and this, even though this is not shown here, this analytic theory, but it kind of is on top, yeah.
Very interesting. I have more questions, but I might ask later.
So what I understood is that what is limiting the fact that in the mode insulating phase you don't see the burst or like the acceleration is the effective coherent length, no? You were saying.
Yeah.
So what is limiting, and if you have some ideas of that you can extend it like in future experiments?
So basically, I mean, we have the issue that in order to make a mode insulator, yeah, you need to confine your atoms really strongly. You shouldn't have tunneling along this direction, yeah, but you should also have enough interactions. And so to do that, we basically went into a situation where the tubes are very, very confining, yeah, something like 40 recoils. And in that case, the coherence length that you get in those tubes is limited.
But there is no ways of like...
You can. I mean, basically, what we were limited by here was a limited laser power along this direction, yeah, so we couldn't make the tunneling kind of small enough, yeah, so we had to increase the interactions instead. But since then, we have basically more powerful laser now, and so we can do these experiments by just making the tubes not so deep anymore. And then we should sort of at least get closer to this expectation that something speeds up.
And also maybe one more, like, so did you try, because you could get directional emission, no? You were showing with a single emitter, like have you thought about studying the collective behavior also, like here, with the directional couplings, like what would be the equivalent of Arno's superradiance, no? Kaira superradiance, but here? Did you try, or?
I mean, our system is not by nature chiral, yeah. So,
sure, but
so all you do is you prepare you put some momentum in your initial state, yeah, and then this momentum, because everything is energy and momentum conserving in the end, the momentum translates to the matter wave.
But you cannot extend this control to the multi-emitter situation, like.
So in this case, you have a mod insulator. If you put a phase on, it doesn't have any effect. Yeah. So
true.
Yeah. So you need to basically already be a little bit coherent in order to be able to imprint something. Yeah.
I see.
But I mean, you could use this basically as a new method, let's say, to probe the superfluid to mod transition to see whether your emission is imbalanced or not. Yeah.
Okay,
So,
thanks.
Yeah.
Yeah, so going back to this absence of seeing the superradiant burst from your mod insulator, it seems like there's several things going on. One is your photons are effectively very slow, right? So they don't actually leave the system,
Right.
and that's different from the old description of Dicke superradiance. I mean, that's an interesting situation, and that's something you can control by changing your Rabi frequency, right? Like that they.
So the speed is controlled through the detuning. So we can basically
detuning.
go, yes,
Right.
we can go to large
Right.
detuning and crank
Yeah.
up the Rabi
Yeah.
frequency so that we still
Yeah.
have significant
I see.
coupling. Yeah.
And then the second thing you have that's different from the old description of Dicke superradiance is your photons are interacting with one another.
Right.
So you have photon-photon collisions, and that's where you started talking about this Tonks gas. So I don't know if there's been a lot of treatment about Dicke superradiance in the case where photons interact with one another, but that seems to be an interesting situation. And then the third one, which I guess I wouldn't see an equivalent in regular quantum electrodynamics, is that your photons are scattering off of excited atoms. Is that right?
That is not completely negligible. So the scattering of the photons of the excited atoms, that describes a collision between an atom that's propagating in the tube and an atom that's stuck in a lattice well. That is relative. I mean, it depends on the energy of emission. So the height of this bump is on the order of 0.1 recoils. Yeah. But if you emit at 4 recoils, it's basically a small perturbation. But I cannot exclude that that's something that complicates the situation. Now, the interaction between, or correlations between the photons, I mean, what you run into very fast is basically a effective, let's say, mean field picture, where in some sense you form a interacting gas of atoms in the tube, and if the tubes are not strongly confining, that would sort of be a superfluid. And so now this excitation is no longer decaying into the vacuum, but it starts to sort of be coupled to a superfluid, and it becomes a completely different model. So in the sense that you have a spin now that's coupled to a superfluid with some mean field, and you will form dimples, and you will get polarons and so on. So it's more, it goes, this model of this Weisskopf-Figner model crosses over into a spin boson model very quickly, and then so it leaves sort of the nice well-defined kind of theoretical description relatively fast.
So I have a question on whether the superradiant behavior would change if you have defects in the Mott insulator.
So
like
you're seeing a hole in the Mott insulator. That's a very good question. I'm afraid I might not be able to give a nice answer. I mean, basically what you could say, let's consider a situation. We have a Mott island here and have another one there, and there's like a big distance between them. Now it matters how fast the coherence builds up here with respect to how long it takes to communicate. And so I think this is not entirely kind of clear to me where you sort of would be able to say I have two different samples or whether there's just a defect there. So I think if it's just a missing atom, it probably will not make much of a difference.
But it can play a role like a vacancy in solid state bulks.
Yeah.
So would you like to give an idea of what you have in mind if you take fermions instead than bosons for studying superradiance?
Yeah, so actually there was a paper from Sirac's group not too long ago. What happens when you do these experiments not with Bose-Einstein condensate to start with, but with a Fermi gas, And so, I mean, basically what you see is that, of course, the superradiance is much suppressed, simply because you cannot build up the same amount of coherence.
Are there questions or to ask before the coffee break? One last.
the gravitational field aspect that you were talking about, are you accounting for the fact that as the matter waves go up and down, there will be some red and blue shifts, and is that what is causing the asymmetric interference?
So what we do, I mean, this is very interesting. You could sort of do the emission while the Bloch oscillation is going on in the tubes, but that's not what we do. What we do is we turn on the gravitational gradients for a short time, and then we turn it off again. Yeah? So we just imprint the phase gradient. So this is not a dynamical change, but this would be very interesting to sort of
vertically, and then look at the super radiance of when you have a correlated pair of atoms, and the photons going down will be blue shifted, the ones going, not photons in this case, matter waves, blue shifted and red shifted, which will create some asymmetry or imperfection in the collective emission behavior that could.
I mean, that's the thing. The atoms are not only heavy, they also, I mean, they're not only inert, they're also heavy. So you have to be careful actually when you emit that you sort of don't emit going the hill up or down. You would immediately break the symmetry. And,
that would be from the perspective of like, it could measure the field gradient if one were to think of, sorry.
And now I say this is a fantastic comment for going into the coffee break and
talking about more. Okay, thank you.